We've been talking about ideal gases. Let's talk about real gases. So an ideal gas has no attractions between gas particles, and the particle volume is negligible. So we got that from kinetic molecular theory. Under many conditions, real gases behave very much like ideal gases, so much so that we can ignore the differences. So here we've got, this is occurring at STP, standard temperature and pressure, comparing the molar volume of different gases. Here's the ideal gas, 22.41, and here are several real gases. Chlorine, 22.06. That one is the most different, and yet it's still pretty close. And then we've got things like helium, which is behaving exactly the same as an ideal gas at standard temperature and pressure. But if we get to high pressure or low temperature, then we do start to see differences. So at a low pressure, there's lots of space between the particles, and the particle volume doesn't matter. So the molar volume of a real gas will be pretty much the same as an ideal gas. If we squish this gas, though, we increase the pressure and increase the pressure. Eventually what's going to happen is we're going to squeeze them so close together that they're actually touching each other and cannot be squeezed anymore. At that point, does the volume matter? It matters a lot, right? Well, somewhere between here and squished so much that it becomes a liquid, we see that the molar volume of the gas no longer behaves the same. So as we squish these together now, the size of the particles becomes more and more and more important. And so we see that the actual volume is greater than what's predicted by the ideal gas law. Because as we squeeze the particles closer and closer together, their volume occupies a larger percentage of the gas volume. So we could look at that. Here's molar volume versus pressure. In the red is an ideal gas, in the green is argon. And here at low pressures, and this is atmospheres, 200 atmospheres is really high. And 1,000 atmospheres is just mind-boggling. It's really, really high pressure. So at low pressures, they behave the same. But as we increase the pressure, we see that the volume of argon is larger than predicted. Because real gases, their particles do take up space. Yeah. Temperature is a factor as well. This is at a high temperature. We're going to see that if you go to very low temperatures, things get wonky as well. 1873, Johann van der Waals, was interested in this, and so he added a term to the ideal gas equation to compensate for this behavior. So that adds a term. This constant here is going to be different for each gas. So if you need to calculate the actual volume of a real gas, you can do that. We're not going to do it. We also have an effect of temperature, and this is because of intermolecular attractions. At high temperatures, we see that the pressure of a gas is the same as predicted by the ideal gas law. Because at high temperatures, gases have high kinetic energy. They're running into each other quickly and bouncing off. They don't have any time to interact. At low temperatures, the gases are moving more slowly, and now when they bump into each other, they might notice each other and become attracted to each other. You have a chance for like a conversation maybe, and then, ooh, hey. And so that affects the interaction, right? They're going to kind of stick a little bit. They're not going to bounce off as easily. So the weak attractions between particles now become significant. And that causes the actual pressure to be lower than what we would expect. So here's a graph of that. There's pressure versus temperature. And so freezing point of water is in here somewhere. At high temperatures, the behavior of xenon and an ideal gas is the same, but as we get to lower temperatures, now we see a bit of difference. The xenon has a lower pressure than predicted by the ideal gas law. Van der Waals also added a term to the equation to compensate for that. It's got a different constant A, and if you needed to use that, you'd go look it up in a table. We're not going to do it, but it's there, so I'm supposed to tell you about it there. You've been told there's an equation for that. These are the constants in a table. I don't know why he even bothers to put these in the book, because I guess the benefit of looking at this, the Van der Waals equation, is it makes the ideal gas law look pretty simple in comparison, right? So, we look at all these gas laws that we've been using, and we look at this one and say, well, it could be worse. At least we don't have to do that. Yes?
So what you're saying with all of this is that even if you put that really high pressure or that really low temperature into the ideal gas law equation, you would get like a good reflection of how the gas is actually behaving?
Right. So at extremes of temperature and pressure, the behavior predicted by PV equals nRT will not match up with what you actually observe.
Even though you're putting in those values?
Right. Yeah. You're putting in the correct temperature and everything. But because the ideal gas law doesn't account for gases actually having a volume, the particles, or for them being able to attract each other, then it doesn't work. But the great thing is that under many conditions, it works well enough, and it's so much simpler than this. But of course, if you're designing rockets or other, very technical things at extreme conditions, you have to take those things into account. So this is the behavior of real gases compared to ideal gases. It's kind of a strange graph. Here we have PV over nRT. So that should be the number of moles, right? 1 mole at PV equals nRT. Erase that whole sentence. So in this graph, an ideal gas will give us a straight line, because PV over RT should be the moles of gas, and that should be the same regardless of what the pressure is. But with real gases, we see deviations. So here, helium, this value is higher than predicted by the gas law, and for things like water, it's lower. So curves that are higher tell us that the most important factor there is the size of the particles, and that's going to be true for these noble gases, because noble gases really are not attracted to each other at all. If we look at water vapor, water molecules are significantly attracted to each other by hydrogen bonding, and so the biggest effect here is the attraction between the particles, and that causes this value to be lower. So this is graphing 1 mole of gas under different conditions.
When you speak upon attraction between the gases,
Mm-hmm.
are you referring to like them touching each other?
So when they collide with each other, there are forces that attract them to each other, and those are the forces that are responsible for the existence of solids and liquids. Because why is water a liquid at room temperature? Why doesn't it fly apart as gas molecules? Because the particles
So
are
it's that
attracted to each other.
attraction that's holding them.
And we'll learn more about the different kinds later.
And the attraction is because of high pressure and low temperature? Like both of those cause
It's the low temperature that causes it. Right. It's hard to explain from the graph. Yeah. It's a graph that's a little hard to understand.